Just put the camera a little down, please.
Down.
Yep.
Is this
Yeah.
down? Yeah? This is
Yeah, that's right.
okay. That's what I wanted to know, but I can't see myself, so I couldn't figure
Yeah, no,
out.
this is fine. Just put the camera a little down, please.
Down.
Yep. Yep.
Is this
Yeah.
down? Yeah? This is
Yeah.
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 Yeah? This is
Yeah, that's right.
Oh.
Down, please.
Down.
A little down, please.
Down.
Yep. Just put the camera a little down, please.
Down.
Yep.
Is this
Yeah.
down? Yeah? This is
Yeah, that's right.
okay. That's what I wanted to know, but I can't see myself, so I couldn't figure
Yeah, no,
out.
Is it okay if we wait for 3-4 more minutes? I think people are still joining.
Sure, sure. Take your time.
Just put the camera a little down, please.
Down.
Yep. Yep.
Is it
Yeah.
down?
Good evening, everyone. I, Amrita of Virtual Nobel Evenings 2020 on behalf of the Science Club IISER Pune. Thank you for turning up for this. I really hope this talk series will help you gain some useful insights on paradigm shifting research that led to this year's Nobel Prizes. It would be nice if you can get the queries only after the talk is over. Feel free to unmute and ask them or put them in the chat window. Meanwhile, our audience questions in the live chat during the talk, and we'll take them up after the talk is introduced. Our first speaker of the day, Dr. Vineeta Pune, is a notable immunologist of India. She started with an MBBS and an MD, but later shifted to basic research instead of practicing medicine. She did her postdoctoral research at the Royal Postgraduate Medical School in London and later joined as a scientist in the National Institute of Immunology. Her work has been focused on understanding pathways regulating the fate of T lymphocytes in immune responses using mice and humans as the appropriate model systems. Now, I would like to invite ma'am to take over and deliver the first talk of the day on the Nobel Prize in Physiology and Medicine 2020.
Thank you, folks. I'm so glad that these talks are getting organized and there is audience in the IISER and I hope outside IISER too. So this is today's, and those of you who were present yesterday have heard from Girish Ratnaparkhi, a colleague of mine, about while the discoveries of Emmanuel Charpentier and Jennifer Doudna, who are occupying the primary space on this slide, are of great significance, it is noteworthy that in the history of 120 years of Nobel Prize, never ever had two women become laureates. For peace and literature prizes, women's presence is already noticeable. But their near absence in physics, chemistry, and physiology or medicine. The number of women in natural science prize has a special status in the mind of many women. Women scientists can certainly can and should aspire to Nobel laureates. What you see on the slide are 4 women and 5 men. So while this is coming close to each other, the prizes, the literature prize, as I said, is quite often given to women as well. So, as you know, Alfred Nobel wrote in his will, and I quote here, "Those who during the preceding year shall have conferred the greatest benefit on mankind," and unquote, will be considered for the prize. However, his notion of conferring greatest benefit on mankind meant that the discovery should not only be significant, but it should also prove useful for the human beings. This process of proving useful and being accepted widely as useful is normally a very long-drawn process. And hence, in most cases, you will see a lag of many years before the discovery, between the discovery and the selection of individuals for the prize. This year's prize in physiology or medicine, given to Harvey Alter, Mikhail Houghton, and Charles Rice, is no exception. Of course, as you know, it was given for the discovery of hepatitis C virus. In late 80s, hepatitis C virus was discovered, and 30 odd years later, the Nobel Prize for its discovery was announced. Alter and Rice, the 2 Nobel laureates, work in the United States, whereas Houghton scientists contributed in very different ways to make the discovery complete. And in brief, it is shown in this title, in this slide. But let me give you some background which will provide significance and work. Today, we think of blood transfusion as a piece of cake. A healthy donor goes to a blood bank. It is he or she is treated as a replacement donor, and a blood pack already collected from another donor is normally given to the recipient. In today's date, fresh blood taken out of one donor to a recipient. Well, of course, in places where infrastructure for a well-equipped blood bank is not available, such direct transfusion is still occasionally practiced, but it is of disease transmission. People had noticed that blood transfusion led to many instances of post-transfusion hepatitis. So recipients suffered from jaundice and associated discomfort. Most of them recovered, but some continued to suffer from hepatitis. Hepatitis A and B were clearly identified in the 1960s as separate viruses, and it became known that hepatitis B and not hepatitis A is transmitted via blood. Baruch Blumberg won a Nobel Prize for hepatitis B discovery in 1976. Soon, a diagnostic test was developed to see virus, and all bloods showing positive tests were discarded. Expectation of the scientist at that time was obviously this test would help in elimination of hepatitis. It did not. And these kinds of disappointments are very common if anybody is pursuing science research medicine. The incidence of hepatitis go down, but still a large number of people did develop hepatitis, and not just hepatitis, but also developed liver cirrhosis, and even a smaller number of cellular carcinoma or liver cancer. So this was a real problem in clinical medicine. Alter's work was related to this virus pathology. Neither A nor B, but a virus. In fact, in 1980s, the unknown virus was actually called remaining cases of transfusion hepatitis, or more than one viruses can be identified. As it happens, hepatitis viruses, at least 2 viruses were discovered. And I was working on the epidemiology of early mid-80s. Not necessarily transfusion-associated jaundice. I mean, the research work that pursue the work further, but at least hepatitis have since been discovered. I certainly am sure that what we were encountering as hepatitis was hepatitis E. And it was responsible for causing fulminant hepatitis and pregnant women dying due to that. But well, that's just an anecdote, or the hepatitis C virus responsible for further discoveries. Now let's move from anecdotes to real information. We are still talking about 1980s. Even polymerase chain reaction, or PCR, developed as a technique then. Forget about CRISPR-Cas9 discovery, which is one that bagged the Nobel Prize in Chemistry this year. Newton used an unusual virus from plasma, which came from patients suffering from hepatitis. In 1980, in Chiron Corporation, human chimpanzees and Newton isolated from infected chimpanzee blood. Mind you, this was before human genome was sequenced, or RNA sequencing were available. Efforts for long periods led nowhere. It was apparently extremely frustrating. Dr. Ki Len Chu and Dr. George Kuo and his collaborator in Daniel Bradley at CDC were also working along with Newton to discover these samples, to discover the virus, so-called virus. They were provided. They discovered multiple viruses. One full clone of the virus belonging to Flaviviridae family. This family has many human pathogens that we know of. Dengue is a particularly dengue, Japanese encephalitis, Zika, yellow fever, all belong to Flaviviridae. I'm part of the science discoveries and prizes here. The highest award in the world, possibly because by now, of course, it is a 120-year-old tradition. Livelihood awards also fall into alternate Nobel Prize categories. They are relatively younger ones, not more than 100 years old. Nobel Prize award say that not more than 3 scientists can be awarded the prize. 10 choices. Every year, one hears that not just the awardees, but their colleagues equally deserving the prize were denied the honor. This year is no exception. Newton has expressed his unhappiness to the colleagues that I mentioned. He had said Without their contribution, this discovery was not possible. He has also turned down 1 or 2 earlier awards because his colleagues' contribution was not acknowledged. I do see a great acknowledgement and recognition of a team spirit here, which is becoming more and more essential in the modern science research practice. As I said, with rapid advancement of technology, one scientist cannot be expert in many fields, and many more people are required to answer research questions. So extensive long-term collaboration between scientists with complementary expertise is considered necessary. This was, of course, not the case when Alfred Nobel left the money in his will for these prizes. But what he has written in his will cannot be changed, because who has the authority to change it? I hope somebody has. Anyway, as a result, it has become necessary to rethink about not just prizes, but those who do not.
Ma'am, sorry to interrupt you here. Can you please tell at which slide you are right now? Is it slide 4?
No, I'm describing which is this slide number. This is slide 4. This is slide 4.
Yes, ma'am. Thank you.
Yeah, slide 4, I hope.
Yes, ma'am.
Yes. So, where was I? Science, it is what enthusiasm for pursuit of scientific questions should be the basis of your research endeavor, and the primary reason for your sustenance. Let's see what we have moved to the third blue. We have moved to the third blue circle, if you please. This slide says rice provided the final evidence and caused hepatitis. What does that mean? Let me explain his work on the basis of what are described as Koch's postulates. So I'm moving to the slide number 5. There are 4 postulates which I have listed here. These were established in the 19th century by Robert Koch, and we still call them as postulates. Koch, along with other colleagues of his at that time, evolved these to establish causative relationship between a microbe. He showed them to be true for cholera and tuberculosis. Both these diseases are of bacterial origin, rather than elaborate on all of those, but we'll still talk about them. I'm sure some of you who have done microbiology as a subject might be familiar with these. The first principle, listed as number 1, isolate the microorganism from the disease. And the organism should not be present in healthy individuals. While this sounds logical, in some cases, there are so-called healthy carriers of the disease, and with modern technological tools, not in the 19th century, their carrier state can be established. The second point, which means the first postulate is not 100% accurate, is that the microorganism must be cultured from the diseased individuals. Here we run into some problems in the present context, because as you know, bacteria can be cultured in a medium outside the body, but viruses are not in that sense culturable. We can isolate RNA, for example, from this virus, from a patient suffering from hepatitis C mediated hepatitis. But growing is more of a problem. We do see footprint of the virus, say IgM antibody and so on and so forth, but actual growing of the virus is fraught with some difficulty. For example, we still cannot grow hepatitis E virus reliably in culture, though we know a lot about its pathogenicity. Hepatitis C virus can now be grown in hepatocyte cell lines, but that is not what Koch meant when he said must be cultured. Third postulate is now about inoculating the microorganism to a healthy human being to reproduce the original disease. I have put animal with a question mark in front in that statement. In today's world, we have evolved principles of ethical research. These principles have evolved after Jews were experimented upon during the Second World War time. Really horrible experiences they went through, or Black people were infected with certain infectious agent and were not provided treatment so that natural course of infection could be understood. You can imagine the horrific situations that these groups of people must have undergone. Koch actually wanted a proof of that kind and the illness. But we don't really accept that in today's age and world. You must have heard about clinical trials. Everything about COVID drugs, COVID vaccines gets talked about. So I'm sure you're familiar with clinical trials. And how only those individuals who provide consent after understanding the risks and benefits of participating are experimented upon. Thus, there are stringent restrictions on experimentations on humans, and fulfilling this postulate the way it is visualized in the 19th century is pretty much impossible. That is where the bracket with the word animal is relevant. In controlled ways, we can experiment on laboratory-reared animals, laboratory-bred animals. They are maintained and bred primarily for experimentation. They are not wild-caught animals normally. Rice performed these experiments. So that is why I had brought in the Koch's postulate. He used purified virus to infect chimpanzees. Chimpanzees don't have hepatitis. He went ahead and provided data for the fourth postulate, that the microorganism must be re-isolated from the inoculated diseased individual. In this case, it was from chimpanzees. The original virus sequence and the one isolated from the infected chimpanzees were the same. Thus, the three investigators who received Nobel Prize actually together over a long period fulfilled Koch's postulates. So this was about the prize, the discovery, and the discoverers. Let's now understand why this discovery turned out to be of great public health importance. What was the benefit of to the humankind that Alfred Nobel was keen on? As I mentioned earlier, the blood transfusion as a technology to save human beings has been in existence for many, many decades now. But as its popularity and use increased the number of people facing consequences, such as post-transfusion hepatitis, the problems went up significantly. A large number of these individuals continue to suffer from chronic hepatitis. Chronic inflammation of liver essentially destroyed large functional parts of the liver, leading to these stages are the ones which are being described or shown, depicted on this slide. Cirrhosis of any origin are more prone to develop liver cancer, as has been well documented by now, and both hepatitis B and C viral infections do contribute to liver cirrhosis and liver cancer. Blood transfusion used as a treatment for some form of morbidity is not something that we accept. In the 1980s, the world also discovered presence of HIV, human immunodeficiency virus. That could also get transmitted via contaminated blood and hence cause post-transfusion, not hepatitis, but HIV/AIDS. Free of all contamination, a major challenge, and discovery of hepatitis C virus contributed to answering this particular challenge. Sorry, something happened? I'm sorry, I'll just come back here. Yeah, something happened to my... Can you see the slide still?
Yes, ma'am.
Okay, one sec. Something happened on my laptop, so I wasn't sure whether you can see the slides or not. Okay. But I can't because I will have to change. I'm sorry about this. Okay, now. So this So I was talking about the discovery of Nobel hepatitis C contributing to this challenge. So the cartoon that I'm showing you right now is the cartoon to describe long-term progression of liver pathology resulting in cirrhosis and carcinoma. But essentially, the discoveries by 3 Nobel laureates and their colleagues resulted in the development of a good laboratory test for the presence of hepatitis C virus in the blood. From 1990 onwards, these tests to screen for hepatitis C virus are available. By 1996, the screening resulted in an annual reduction in cases due to hepatitis C by 80%. The map that I'm showing is a 2014 map, and you will see very light blue colors to very, very dark colors. Very light blue colors are showing incidence of in less than 0.6% cases, and very dark colors, as in what you can see in old USSR, is or in Egypt or Pakistan, wherever you can look at. Those are the places where the incidence of hepatitis is 2.9 to 6.7%, which is very, very high. In India, the incidence is between sort of 0.5 to 1%. So we fall into the pretty much low level of the infection. But still, despite what I was talking about, the diagnosis available for hepatitis C before transfusion, there are reports which mention that about 71 million people globally have chronic hepatitis C infection. And obviously, they are at risk of developing liver cirrhosis and liver cancer. Apparently, I shouldn't say apparently, data, 1.4 million people die globally from hepatitis C and its associated complications. So the numbers are not really small. In India, screening of blood donors for hepatitis B, C, HIV, malarial parasites, syphilis, etc. is recommended. But as I said, 0.5 to 1% of all individuals in India show evidence of hepatitis C virus, though we don't really know exact numbers of HCV-induced carcinoma. We also, these data are available from the donors who come for blood transfusion. So overall incidence in the population is also not quite known in India. I'll mention sort of one last point, which is very peculiar about decreasing global load of hepatitis C before I stop. There is still no vaccine that has been developed to prevent hepatitis C infection. Unlike hepatitis B, for which there is a very effective vaccine, and it is part of universal immunization program in India too. However, there is effective antiviral treatment for hepatitis C with direct antiviral drugs. Viral infections which are of chronic nature, such as HIV infection or HCV infection for that matter, there is possibility of having effective antiviral drugs. And I'm saying this very specifically because currently we are in the phase of COVID-19 epidemic, which is acute viral disease, and there are very few effective drugs for acute viral infections in any case, and we have already heard about remdesivir, which was touted as very, very effective, being only marginally effective, if at all. So the difference between chronic and acute viral infections is very clear. Hepatitis C viral infection, if it becomes a chronic infection, then there are drugs, and because of which a lot of cure has been achieved even in the absence of efficient vaccine. And even for HIV, I'm sure you know that there is a near success and cure with antiviral drugs. Thus, this discovery of the virus, proving Koch's postulates and developing drugs to cure the chronic stage of infection together are great discoveries which have provided relief from human suffering, and hence certainly fit the bill for the Nobel Prize. And I would say this is a prize which is both for understanding the physiology of viral infection and its treatment as in medical options. Thus, a prize in physiology and medicine. Reason I say this, in chemistry, there is no either or in it, but this particular prize is normally declared as either physiology or medicine. I think this year's prize is for physiology and medicine. Thank you very much.
Thank you very much, ma'am, for that talk. The floor is now open for questions. Please feel free to unmute or put your questions in the chat window.
I have a doubt. Thank you, ma'am, for the amazing talk, first of all. So I was from this map, I was wondering, so it's surprising to me that India has escaped a lot of, we still have less number of cases. So is it because of the screening, like you mentioned, or is there some other reason why we, even after we have so much population, still it has...
Well, as I said, both options are open. India is not known for having good epidemiological records and numbers for practically any disease, not disease, but for any disease. Our governments have never insisted on having hardcore epidemiological data for pretty much any disease. Incidence is low only in the, is as low as has been depicted, or it is underrepresented. I can't really give an answer. I have because I'm not aware of large scale or like national sample surveys are done on a subset of individuals. That kind of survey being done for checking in incidence of hepatitis C in general population. There is also a problem in the sense how hepatitis C gets transmitted. Of course, it gets transmitted by blood transfusion, but whether it is very actively transmitted by sexual transmission is still unclear. So a few things do need for hepatitis C as well, but I suspect the low incidence is also partly contributed by not having sufficient data. But the data that we have is mostly coming from the blood donors getting screened. And as I said earlier, if any of these tests come positive, hepatitis B or C or HIV, the blood pack collected is straight away discarded. So based on that, what we have is the information.
Yes, ma'am. So yeah, that makes sense. A follow-up question. So if we compare it with Pakistan or USSR or Egypt, so do they have more screenings going on, or like what is the scenario?
Actually, honestly, I don't know about Pakistan, but for many different viruses, for example, not USSR, Russia, there seems to be a very, very high incidence, so also in Egypt. So is it the case that there were some foci which suddenly helped in spreading, but for a large country which was erstwhile USSR, it's difficult to imagine. But you can also you will be surprised to hear that hepatitis B is also distributed unevenly. So what is the actual reason? What does the biology and the spread of the virus tell us about why it is more localized in some parts of the world as compared to others is very difficult to predict. So in that sense, I don't think I can give you a clear answer saying, yes, this is the cause why USSR or erstwhile USSR is showing such a high incidence. I'm sorry, that's not the case.
Yeah, thank you, ma'am. Perhaps we can look back and see somewhere.
Yeah.
I don't know details about it.
I mean, if I dig enough, I mean, you know very well that hepatitis C is not my terrain of work. So it's not like I have looked at many 20,000 papers on hepatitis C. If I actually do with some clues based on biology why this seems to be the case, but I'm afraid I haven't done that.
Yeah, thank you, ma'am.
Do we have any more questions? Please feel free to put them in the chat window or unmute yourselves. I think we might be done.
Yeah,
Thank
so
you very much, ma'am,
all
for that talk.
I would like to emphasize is the public health importance of the transfusion hepatitis is the primary reason why we have the award given so late after discovery. But that is what Alfred Nobel decided, that there has to be some human significance, and that's why it has come down.
Thanks a lot, ma'am.
Sure.
With this, we come to the end of the first segment of today's evening. I'll take this honor to introduce our second speaker of the day, Dr. Suneeta Vardarajan, who is an associate professor of physics at IISER Pune. Ma'am obtained her PhD from the Institute of Mathematical Sciences, Chennai, and prior to joining IISER Pune, she held various positions in LMU Munich, University of Alberta, and University of New Brunswick. Her research interests lie in the interconnected fields of gravitation and mathematical physics, dealing with problems on classical black holes. Now, I would like to invite ma'am to take over and deliver the second talk of the day on the Nobel Prize in Physics 2020.
Yeah, thank you very much. And thanks to the Science Club for asking me. So I hope you can see my screen now. And I'm just going to open my presentation. So let full screen mode, and let me go to the slide, which is okay. So hello everyone. So what we are going to be talking about now is the Nobel Prize in Physics 2020. And as you all know, as you've all read, the Nobel went to the black holes. So before I go to black holes, I just want to show you this very famous image. This is an image of a black hole at the center of a nearby galaxy called M87, imaged by the Event Horizon Telescope. So you can see that the most luminous parts are seen in yellow, and there is a black core. So let us just start with a working definition of what is a black hole, because that's what the Nobel has gone for. Okay, so we'll start with this working definition and we will get more precise as we move along. So black holes have been conceived of from the 1700s as objects with a gravitational pull which is so strong that not even light can escape. And that's why, how do they form? They are typically burnt out stars, or they are formed from several such stars which merge together, typically with a mass many times the mass of 30 solar masses or million solar masses. You have the entire range. And the most important thing is that they are characterized, is not the surface of the star, okay, but it is a surface in space which acts as a one-way surface. Matter and light crossing it to go inside can never return outside. So these strange objects are what the Nobel has been given for. So let's just go to the people who've got the Nobel. One half is gone to the two astronomers whom you see in the second and the third picture, Reinhard Genzel of the Max Planck Institute for Extraterrestrial Physics, and Andrea Ghez, who's a professor at the UCLA. Now, these people are astronomers, and what they got the Nobel for, one half of the Nobel for, is for actually probing the center of our galaxy, which is the Milky Way, and for the discovery that there is actually a supermassive compact object at the center, and which is, most likely a black hole. Okay, so these people are astronomers who got this for, at the center of the Milky Way. The other is Roger Penrose. Now, what Roger Penrose got this singularity theorem and formation is very natural in the correct theory of gravity, which is, I'm going to start with the work of the astronomers first, to probe the center of the Milky Way. And the question is, what lurks at the center of our galaxy? So I should just mention here, I'm not an astronomer, I'm a theorist myself, but I will try to do justice to their work as much as I can. Now, this group of Genzel and the group of Ghez have been actually working from the 1990s, which is a very long time. They've been doing painstaking astronomical observations from the 1990s. And they've been studying the center of the Milky Way in a region called Sagittarius A star. Well, this is just roughly the center of the Milky Way, and there are radio emissions coming from this region. So what they did was they studied the center. In particular, they looked not at light, whose wavelength I have given here, and they looked at the light coming from this region. Now, the problem with visible light is that because you have the stellar atmosphere and you have the Earth's atmosphere, only 1 in about 10,000 particles of light, they are visible light photons. Right? About 1 in 10 reaches actually do to answer the question of stars. Okay, so if you want to know what is at the center, you want to know how things are moving around the center. What they did was they tracked the motion of nearly 100 stars around the center of the Milky Way. Now, this is not an easy task. These stars are very far away. Okay, and you have a lot of atmosphere, you have the stellar atmosphere, you have the Earth's a lot of flicker. If I look at the star for a second, that's okay. But if I want to actually track its entire orbit, then that's a lot of work. You have to be very precise. So first, what they did the early 1990s, which is short exposure pictures of these stars. And then you take lots of such pictures and individual star orbits to figure out what is the star's orbit. But that was not enough. And then later they started using such as, for example, adaptive. Now, what you do to actually image the star with longer exposure times. Okay, so what you do is basically you actually create an artificial star. So what is the problem? Your star twinkles. That's the problem, right? So there's a lot of distortion in the star's actual position due to the atmosphere. So what you do is you actually create a point source of light close to the star in the sky. So what you do is you take a laser and then you excite sodium atoms in the upper atmosphere. Now, when these excited sodium atoms emit light, they emit light like a point source. Okay, so this is your laser guide artificial star, which is close to the star in the sky. Now, this light, this point source, is distorted by the Earth's atmosphere. Then it's picked up by the telescope. Then what you do is you make it hit a mirror, which is actually deformable. So the mirror is not, it could be just made up of many segments, each of which segments can be moved. To deform the mirror so that your light still looks like a point source. So you correct for the distortion and use that deformed mirror to study the star. So by doing this, you can actually correct for all the distortions, and you can use longer exposure times, and you can track individual star orbits. So they track the motion of nearly 100 stars. This is what I want to emphasize. So what did they find? First, they found the crazy dance of stars around the center. So this is a sort of artist's visualization, but it shows you how elliptical some of the orbits are. And these stars, some of them are orbiting at speeds of about 3 million miles per hour. So they are really fast. They are in highly elliptical orbits and they are very far off. So it's a big challenge to actually track their orbits. Now, what these people found from their observations was, first of all, there is a central object, which is about this many kilometers in radius, 22 million kilometers in radius. And it has a mass which is about 4 million solar masses. One solar mass is a whopping 10 to the 30 kg. Now, using this data, you can figure out what would be the density, what would be the rough density of the central object. Now, what can be the alternatives to having one big central object? You can have diffuse matter, you can have lots of stars, you can have clusters of dark matter. Okay, but we know what the typical densities of all those objects are. We see them elsewhere in the universe. And all those objects have a density which is far less than this density. So the first thing this density tells you is that, no, I don't think these are probably clusters of dark matter cluster or bunches of stars. No, they did more actually. So careful observations which were made over a decade rule out these other possibilities such as matter. And how did they rule this out? There is one particular star, S2, which is in a 15.2-year orbit around the center of the Milky Way. Now, 15.2 years is not so long. Okay, so you can actually do observations for over 10 years, and you can track the orbit of the star. So it was tracked for nearly 2/3 of its orbit over 10 years by both these groups. This star is approximately in orbit and comes very close to the center. Now, you know, solar system, that if you believe in Newtonian gravity, then your sun is this very massive object at one of the foci of the ellipse, and the stars, the planets move in these elliptical orbits with the sun at one of the foci. So that's what Newtonian gravity predicts you, that when you have this compact object, then you have these elliptical orbits around it. So what these people found was the star is approximately in a highly Keplerian elliptical orbit and comes very close to the center. I mean, you have to calculate all the data from the star, and this rules out other possibilities. In fact, it tells you that there is exactly one central object which is very approximately at the focus of the ellipse. So thus, there is a supermassive central object. Nothing which these groups have done. It's amazing work. In the last, seen the orbit of the star S2, and they have figured out that it has an approximate elliptical orbit. The orbit precesses, as I've shown in this picture. This is not a perfect ellipse. This is called a precessing ellipse. Now, in Einstein's theory of gravity, which replaces Newtonian gravity, we actually predict that there are no ellipses. In fact, you will have precessing ellipses, approximate ellipses. This is exactly as predicted by Einstein's theory. So this is lovely work done in the last decade. Okay, now we come to the very important question of what can a supermassive central object of this size be? They found that there is this object. What can this object be? Now here you need theory. Here you need the theory of Einstein, and Einstein's theory predicts. So I shouldn't say Einstein predicted, I should say Einstein's theory predicts that if the radius of the star is less than this number, which is 2 gm by c square, which is basically some fundamental constants times the mass. This number has the dimensions of length. So you can compare it with the actual radius of the star. Now, if the radius of the star is less than this number, then the object is a black hole. And this is indeed true for the object at the center of the Milky Way. So it has a radius which is less. Now, black hole has a horizon at this radius, which is a one-way surface. Nothing that crosses this surface inside. So this I just want a rich feature of a black hole. So what the theory tells you is that this supermassive central object is most likely a black hole. Now, what more can you say Now, what happens is that if you have black holes which are so massive, then they can actually start to collect matter around them at this radius called RS. These are called accretion disks, and these accretion disks form at the innermost stable circular orbit. So the matter is very stable when it's at this radius. Now, if as it falls into the black hole, it moves very fast and it heats up and it emits these short infrared have been observed from this region close to the central object. So the most reasonable explanation that fits the data so far and is consistent with theory is that there is, right in the beginning, was an image of a supermassive black hole in a nearby galaxy called M87. We have seen such supermassive black hole. In the process, people are in the process of imaging the black hole at the center of our galaxy as well. So Gers and Genzel got 1/2 of the Nobel for this beautiful work. So here I'm just going to show you an artist's representation of what such a black hole would look like. It would be all black in the inside because light is trapped. So the event horizon is the accretion disk at about 3 to 5 times the radius RS. Okay, so this is what a typical image would look like. But now, theory in a very crucial way to argue that this object is a black hole. I want to delve a little bit more into theory now. I want to delve into the remarkable contributions of Roger Penrose. Now, here in this picture, you see Roger Penrose standing